In this video, I'm going to show you how to calculate or solve problems involving redox titrations. In this problem, a 50 ml sample containing lanthanum ion was treated with sodium oxalate to precipitate lanthanum oxalate, which was washed, dissolved in acid, and titrated with 18.04 ml of 0.006363 molar potassium permanganate. Calculate the molarity of lanthanum in the unknown solution. Okay. So since we are dealing with a redox titration, we need to determine first the redox reactions. Okay. So let me write down the redox reactions involved in this titration. So first, you have permanganate. So permanganate will react since this is usually done in acid solution. So permanganate will be converted to manganese 2 plus. Okay. Now, balancing this reaction according to ion electron method. So there is 1 manganese. We have 4 oxygens. So we need to add 4 moles of water. On this side, there are 8 hydrogens. So we need to add 8 H plus. And we need to balance the charges. So here you have a charge of positive 2. Here you have a charge of positive 7. To balance the charges, so we need to add here 5 electrons. Next, the oxalate will be the one being titrated. Okay? And it will undergo oxidation. So your oxalate, C2O4 2 minus, will be converted, since this is in acid solution, this will be converted to carbon dioxide. Okay, so again, we balance the carbons. So this is times 2. And we have also balanced the oxygen. Next, we need to balance the charges. So this has a negative 2 charge, and therefore we need to add 2 electrons on this side of the equation. Okay. Now, there are 2 approaches to this problem. Okay. What we can do is to add these 2 reactions in order to determine the overall balance equation. So to do that, we need to balance the number of electrons lost should be equal to the number of electrons gained. Therefore, this reaction will be multiplied by 2, and this reaction will be multiplied by 5. So that you have a total of 10 electrons lost, and that is equal to 10 electrons gained. Therefore, the overall balance equation will be 2 moles of permanganate plus we have 5 moles of oxalate plus 16 H plus. We will now cancel the number of electrons. Then it will produce 2 moles of manganese 2 plus. We have plus 10 moles of carbon dioxide plus 8 moles of water. Okay. So now, again, using number of moles, So here, we can use moles or millimoles based on our stoichiometry number of millimoles of oxalate is equal to the number of millimoles of permanganate multiplied by our stoichiometric factor. Okay, so we have here 5 moles of oxalate divided by 2 moles of permanganate. Okay, so now we can get number of moles of oxalate based on the number of millimoles of permanganate. So number of millimoles of permanganate will be molarity times volume in ml of permanganate multiplied by our stoichiometric factor. Again, 5 moles C2O4 over 2 moles of permanganate. Okay. Substituting the values, we have 0.006363 millimoles per ml of permanganate times, we used 18.04 ml times our stoichiometric factor. So this is times 5 halves. 5 C2O4, 2 minus divided by 2 permanganate. Okay. So now, number of millimoles of oxalate will be equal to so much millimoles. Okay. Once you solve for the number of millimoles of oxalate, now we look at our again, our stoichiometric relationship. Okay? So from here, we can determine number of moles or millimoles of lanthanum according to the formula of lanthanum oxalate. Okay. Therefore, number of millimoles of lanthanum ion will be equal to number of millimoles of oxalate times our stoichiometric factor. Okay. So according to our formula, since our formula is La2 C2O4 3, so we can say that you have 2 moles of lanthanum over 3 moles of oxalate. Okay, so once you've calculated number of millimoles of lanthanum according to this, okay, please take note that whatever is the value here, you substitute it here. Then finally, you can solve for molarity of lanthanum ion, which is equal to millimoles of lanthanum ion over volume in ml of the solution. Okay. So we know the volume is 50 ml. Okay, so this is millimoles, lanthanum ion, okay, over 50 ml. And that will be so much in millimoles per milliliter. Okay, so again, here, the millimoles of lanthanum will be used here. Okay, now let's try another problem. Now, this problem involves calculation of the iron content in ore. So the amount of iron in a 0.4891 gram sample of an ore was determined by a redox titration with dichromate. The sample was dissolved in hydrochloric acid and the iron brought into the +2 oxidation state using a Jones reductor. Titration to the diphenylamine sulfonic acid endpoint required 36.92 milliliters of 0.02153 molar potassium dichromate. So report the iron content of the ore as percent ferric oxide. Okay, again, the very first thing you need to do is to write the redox reactions. Okay. So what are the redox reactions involved in this titration? So first, you have your iron. So iron, it will be +2. According to the problem, all the iron is brought to the +2 oxidation state. So meaning you're going to start with iron 2 and it will be converted to iron 3. Okay, so this to balance the charge, so +1 electron. Next, the dichromate. In acid solution, your dichromate will be converted to chromium 3+. Again, using the ion electron method to balance this reaction. So we first balance the number of chromium. So you have 2 chromium here, so this is ×2. Next, we need to balance the oxygen. We have 7 oxygen atoms on the left side, so we need to add 7 water molecules. Then we need to balance the hydrogen. So this is plus 14 H plus. Okay. Then finally, we need to balance the charges. So we have here a total of +12. This is +6. So we need to add 6 electrons. Okay. So again, the next step is to add the 2 reactions, but we need to balance the total number of electrons lost should be equal to the number of electrons gained. So we multiply this by 6. Okay, so you have 6 iron 2 plus dichromate plus 14 H plus to form 6.3 plus 2 moles of chromium 3 plus 7 moles of water. Okay. Now, just like in our previous example, what you need to do is to determine number of moles. Let's use moles here. Number of moles of iron 2 plus will be equal to the number of moles of the dichromic Cr2O7 2 minus multiplied by our stoichiometric factor. According to the balance equation, there are 6 moles of iron 2 plus per mole of dichromic. Okay. So again, let's not convert number of moles here, but rather number of moles of the dichromate will be equal to molarity times volume in liters of the dichromate times, again, our stoichiometric factor. So 6 Fe2 plus 1 Cr2O7 2 minus. Okay, and this will give you number of moles of iron 2 plus. Once you have the number of moles of iron 2 plus, then we can determine the number of moles of ferric oxide. And once you have the number of moles of ferric oxide, you can get the weight of ferric oxide in the sample. Okay? Or simply put, you can calculate the weight of ferric oxide based on the number of moles of iron 2 plus. Again, using our stoichiometric factor, okay, you have here 1 mole of ferric oxide will be equivalent to 2 moles of iron. Okay. Of course, we need to convert this to mass, so times the formula weight of ferric oxide, so that you'll get weight of ferric oxide in grams. Okay. So you'll get the weight of ferric oxide in grams. Then finally, calculate percent ferric oxide, which is weight of ferric oxide over the weight of your sample times 100. Okay, so I hope with this guide you will be able to solve your try me. Under redox titration. Thank you very much.